So in this tutorial, we are going to cover the binary tree data structure. In the previous tutorials, we have already discussed about stacks, linked list, and a lot of data structures. And one thing that is common in all those data structure is that they all are linear data structures. So now we're going to study about the binary trees, which is not a linear data structure. And by the word linear means that the data structure looks like this. So if we want to traverse in this type of linear structure, so I'm going to write here linear data structure. So if you want to traverse in this linear data structure, so you will go from one element to the other. So this is a linear way of traversing. So let's study about binary tree. So first of all, I'm going to write here a formal definition of a binary tree. So a binary tree is a tree, or you can just say a visualization. So it's not actually a tree, it's just a visualization of the data as tree, and I will also draw a diagram showing what exactly or how exactly binary trees look like. So a binary tree is a tree whose elements have at most two children. So we will get to this point, what is the meaning of children. So first of all, let me just draw an example of a binary tree here, and let's see how it is different from this linear data structure. So let's suppose I have some arbitrary integer values like 3, 4, 5, 6, 7, 8, 10. So these are some random numbers that I have taken. So if I want to represent them using a binary tree, what I will do is I will first create a first node, and this first node is the top node, and we call this top node as the root node. And this root node will have two children. Two children are linked using two pointers. So this is particularly a simple node which has two pointers. One is the left pointer and another one is the right pointer. So this makes sense because binary tree or a tree is just like it has a root and then it spreads out its branches. So you can see that if this is a simple node, so the first node of our binary tree is known as root, and we will just create two pointers of that are linked with this root node, and each and every node of our binary tree will have the left pointer and the right pointer as well, and these pointer will point to some other nodes. So this means that this root node, this one, has two children. So that's the reason why I am drawing it below this. So let's suppose I am adding 5 and 6 here, and this node, if you are taking this node, then it will also have, it can have at most two children. So at most two children means that a node can have 0, 1 or 2 children. So let's suppose 5 has 2 children, which is 7 and 8. So 4 is remaining here, so let's suppose I add 4 here. So I am randomly adding these nodes as the children of this particular nodes. So I'm just using the left pointer and the right pointer. So this is the left pointer and this is the right pointer. And in this way I am constructing a binary tree. So binary tree is just a root, and the root is the first node of our binary tree, and we can use this to traverse along this binary tree. And a binary tree is just a data visualized, and the element of the binary tree can have at most 2 children, which you can see in this diagram. Similarly, I can add more elements in this binary tree, and this goes on and on. So there will be some point when our data is filled. So the last nodes that you can see here will point to some null reference. So they will point to some null value. Similarly, these will also be null. So this means you can see that at this point, this node has no children. So this node has no children. Since this node does not have any children, we will call it as a leaf node. So by definition, leaf node is the node that does not have any children, or you can say that the children are null. So the concept of binary tree is just like you have one node and you have 2 pointers. One is the left pointer and the another one is the right pointer, and you will just add elements and you will go on like this, and then you will be able to create a binary tree. And the main reason why we are introducing binary trees is because they are efficient in time complexity scenarios. So we know that if we want to traverse in the linear data structure, the cost of the operation is big O of n, and n stands for the number of elements in our array. So a linear structure takes a least amount of big O of n, and you can see that in this binary tree the time complexity is much less, which is in most cases big O of log n, and this is base to the power 2. So the time complexity of traversing is log n, which is less than this. So we know that the value of n is greater than log n. So the time complexity in case of the binary trees is much lesser than this data structure, because let's suppose you want to search an element in this binary tree, you will have to just go down, or you have to recur down. And recur down means that you will use a recursive approach, which we will see in the implementation of the binary tree. I will implement this binary tree in the C++ IDE, in the C++ code, and we will use recursive approach. Recursive is just recursion, which is a function calling itself. So we will see this concept of recursion in the implementation part. At this point, we are going to write some of the properties of binary tree. So let me write some of the properties of binary tree. So first of all, I want to define 2 more terms here. One is the height, and another one is the levels. So the height of this tree which I have drawn here is 3, because you can see that the height is measured like this. This is the first node, and then this one is the second level. So this is 1, this is 2, and this is 1 is 3. So the height of this tree is 3. So let's suppose I have a tree like this. So the height of the tree will be equal to 2. So this was a term that I was going to introduce, and levels are just like this. This is level 1, or some can even use it as a level 0, and this is level 1, and so on. So the height of the tree is 3 in this case, and it can be anything, it depends upon the data. So let me write some formal properties of a binary tree. So the first property says that the maximum number of nodes at any level, let's suppose level L, because we can take any arbitrary level. You can see that this is level 1, this is level 2, and this one is level 3. So the maximum number of nodes, if you want to calculate the maximum number of nodes at any level L, let's suppose you want to calculate the number of nodes that a binary tree can accommodate at any level L. So it will be equal to, this is the formula here, 2 to the power L minus 1. So if I will substitute L with 1, it is 2 to the power 0, and which is 1. So at level 1, we will just name this as level 1, then this is level 2. So at level 1, you can see that there is only one node, which is true because the first node is the root node. So this formula will give us the maximum number of nodes that a particular level can accommodate, and this case is only for binary tree. So the main use of binary tree is that it is very useful in just improving the time complexity of certain operations like searching and insertion and etc. So they are better than these linear data structures. They are also an advancement in data structures. So the next property that I'm going to write here is that if you want to calculate the maximum number of nodes at any level, at any height h, then the formula is equals to 2 to the power h minus 1, and here it was 2 to the power l minus 1. So let's suppose the height is 3 and you want to know what is the maximum number of nodes at height h. So you will just substitute the value of h and you will get the value of the maximum number of nodes. So the third property that I'm going to write is, here is a binary tree with L levels has at least log base 2 L plus 1 levels. So these are the direct formulas. They also have some mathematical proofs, but we are not going through that. We are not going to prove it mathematically. So I will suggest you to note these properties because they are really important, and you will use these properties a lot of time in using in implementing this binary tree. And the last one is that if in a binary tree which has n nodes, let's suppose there is a binary tree which has n nodes, so the maximum possible height or you can say the minimum levels is log base 2 n plus 1. So these are the 4 most important properties that you will have to remember in case of only binary trees, and using these properties you can get the maximum number of nodes or levels. So this is all about binary trees. And so let's now go on to the topic, the types of binary trees. So there are a lot of different types of binary trees that we are going to see, and the main reason why there are a lot of binary trees is because they are useful in performing some different types of operations, and they all are visualizing the data in different manner. So let's now see what are the different types of binary trees. So the first type of binary tree that we're going to discuss is the full binary tree, and the rule says that a binary tree is known as a full binary tree if it has 0 or more children. And if each and every node of a binary tree has 0 or more children, then it is known as a full binary tree. So let me draw an example of a full binary tree. So you can see that this is an example of a full binary tree, because each and every node in this binary tree has 2 children, and you can also see that it has 0 or it should have 2 children. So 0 or 2 children. So you can see that each and every node is having 2 children, and these last nodes are having 0 children because they are the leaves. So this is an example of a full binary tree. The next type of tree that we're going to discuss is the degenerate tree. And a degenerate tree looks like this. And this is null. These all are null. So you can see that in this type of a binary tree, all the left part of this tree is filled with nodes, while the right part has no nodes. You can see that they all are initialized as null. So you can see that this type of a binary tree is, it looks like that this is a linear tree. And this, the cost of operation in such type of binary tree is O of n. And you can see that it looks like a linear data structure. So the next type of binary tree that we're going to discuss is the complete binary tree. So by definition, a complete binary tree is a tree if each node has 0, or I should say that a binary tree is a complete binary tree if and only if all the levels are completely filled except possibly the last level. And the last level can have, or it has all the keys as left as possible. So this definition says that I will draw a diagram of a complete binary tree so that you'll be able to understand this definition, the meaning of this definition. So let's suppose there is a binary tree that looks like this. So this is an example of a complete binary tree. You can see that if all the levels are completely filled except possibly the last level. So you can see that this is the last level. So you can see that it is not filled. This is null. So this last level is not filled, but all the other levels are completely filled because they have 2 children. They all have 2 children. So this is an example of a complete binary tree. So there is another type of binary tree which is known as the perfect binary tree. And a perfect binary tree has two children like this, and the last level can be leaves. So the rule says that a binary tree can be a perfect binary tree if it has two or they should have exactly 2 children. So I will write here exactly 2 children, and the last level can have leaves, can be leaves. So by this you can understand that a perfect binary tree is always a complete binary tree, but a complete binary tree is not always a perfect binary tree. So these are the 4 types of binary tree that we have discussed, and in the next tutorial, we are going to implement the fifth type of tree, which is known as the binary search tree. And binary search tree is useful in the search operations because the time complexity, the time taken by this approach is much less in case of a binary search tree. And binary search tree is type of a custom binary tree. And so let's see exactly what is a binary search tree. So I'm going to write here the rules of the binary search tree. So the first rule is that the left subtree is you can see that if this is a node, for this node the left subtree will be all the elements that is on its left side, and the right subtree is this one. So if in any binary tree, if the left subtree has values, that is, or you can say the keys of the left subtree are less than the node's key. So this is the first rule of a binary search tree. So let me just draw an example of a binary search tree here, so that all the three rules of the binary search tree will be clear to you. So I'm just adding some random values here, but you will see that I am actually following a particular pattern in adding these random values. So I am following the first rule, which says that the left subtree will be always less than any node's key. So for example, let's suppose we are considering this node. It has the value 8. So if we are considering its left subtree, which is this one, so you can see that all the values inside this left subtree is less than the node's key, and you know that the node's key is 8, and you can see that all the values are less than 8. 1, 3, 6, 7, 4 are all less than 8. So if you will pick up any element of this binary search tree, it will follow the same pattern. For example, if I am taking 3 as a node, and you can see that the left subtree is 1 and 1 is less than 3. So the second rule says that the right subtree, I'm going to write it like right st, will be, this time it should be greater than the node's key. So if you will pick up any node in the binary search tree, so the right subtree, the elements of the right subtree will have keys greater than the node's key. So you know that this is the right subtree, and you can see that all the elements inside this right subtree is greater than the node's key, which is 8. So 10, 14 and 13 are greater than 8. So if you will take 10 as an example, you can see that 14 should be greater than 10. So let's suppose I want to add 9 in this binary search tree. So if I want to add 9 in this binary search tree, I will first see that 9 is greater than 8. So it should be placed here. So, and we know that 9 is also less than 10. So I can insert 9 at this position. So 9 is less than 10 but always greater than 8. So if you will follow these two rules, you will always get a binary search tree. So in the next tutorial, I will implement binary search tree in C++, and we will write the if else condition for comparing the node with the value of the left node and the right node, and we will add it specifically if these two conditions are satisfied. And in this manner you can see that searching becomes efficient in case of a binary search tree, because let's suppose you want to search for 14 in this binary search tree. So to search 14 in this binary search tree, you will just compare it with the root node first. So we know that 14 is greater than 8. So 14 will be searched in the right subtree. So the cost of operation is much less because we can avoid all the elements inside the left subtree. So these all will be ignored, and we don't need to traverse in this binary in this left subtree. We will only traverse in the right subtree. So binary search tree is an efficient binary tree in terms of searching. But remember these two comparisons, and if you will follow these rules, you will be able to get the binary search tree. So we will implement this in the next tutorial. So that's all. We have covered the concept of the binary tree and the types and properties of the binary tree. So thanks for watching.